Let's talk about that little blue dot on your map. You know the one. It follows you everywhere, almost perfectly, whether you're in the middle of a packed city or, out in the middle of nowhere. Today, we're going to pull back the curtain on how GPS and all our digital maps actually work. And trust me, the science behind it is way, way cooler than you probably think. So, yeah, that's the big question, right? How does it do that? How can this tiny little chip in your phone talk to something way up in space to figure out your exact spot on the globe? Well, it turns out it's this incredible mix of mind-bending physics, some seriously amazing engineering, and a whole lot of very, very clever data science. Okay, let's just dive right into the deep end with what is, and I'm not kidding here, a truly mind-blowing fact. If you want to understand your GPS, you actually have to start with Albert Einstein and his theory of relativity. Seriously, it's the secret sauce that makes the whole thing work. That's right. The satellites orbiting our planet, the ones that make GPS possible, they are, for all practical purposes, living in a slightly different timeline than you and I. This is all because of two effects from relativity. They're moving incredibly fast, and they're in a weaker gravitational field than we are down here. And because of that, time itself literally moves at a different speed for them. So here's the part that just blows my mind. Every single day, the clocks on those GPS satellites get ahead of our clocks down here on Earth by about 38 microseconds. Now that sounds impossibly small, doesn't it? A microsecond is just a millionth of a second. But in the world of GPS, where you're measuring the speed of light, that tiny, tiny difference is absolutely everything. Get this. If scientists didn't correct for that tiny 38 microsecond difference, the error would just build up and up and up. Within just one day, 24 hours, your GPS would think you were about 10 kilometers. That's over 6 miles away from where you actually are. Good luck getting your food delivery with that kind of error. The takeaway here is just incredible. Without Einstein's theories of special and general relativity, GPS as we know it would be completely and totally useless. So every single time you open up Google Maps or Apple Maps, you are using a practical, everyday application of one of the most profound scientific discoveries in all of human history. How cool is that? So we've got the crazy time-bending physics down, but what's actually up there making it all happen? Well, the best way to think about it is like a perfectly synchronized orchestra, but instead of instruments, it's made of clocks, all floating in space. The whole Global Positioning System, or GPS, is built on this constellation of at least 24 main satellites, and they're all constantly circling the Earth. They're spread out in this really precise way, so that from literally any point on the planet, your phone can see at least 4 of them at any given time. And that number 4 is going to be really important in just a minute. Now, these satellites aren't taking pictures of us or anything like that. Their job is much simpler, but it has to be way more precise. All they do all day long is broadcast a simple signal down to Earth. And that signal is basically screaming 2 things over and over. This is my unique name, and this is the exact time I sent this message. So how do they keep such perfect time? I mean, we're talking about needing insane accuracy. Well, they do it with these onboard atomic clocks. These are the most accurate timekeeping devices humanity has ever created. We're talking so precise, they won't gain or lose a single second in millions of years. And that unbelievable accuracy is the bedrock of the entire system. All right, so we've got these super precise time signals beamed down from space. How does your phone, this little device in your hand, turn that into the little blue dot on the screen? The answer is a really clever bit of geometry. Let's break down the magic of what's called trilateration. Okay, so your phone receives these signals. By measuring the tiny, tiny delay it took for a signal to get to you, it can calculate how far away it is from that one satellite. Now, with just one satellite, you could be anywhere on a giant sphere. Add a second one, and you narrow it down to a circle where those 2 spheres overlap. With 3 satellites, you get just 2 possible points, and your phone is smart enough to know which one is the right one. But that 4th satellite, that's the real hero. It syncs your phone's normal, not-so-great clock with those hyper-accurate atomic clocks, and boom, that's what gives you that pinpoint accuracy. And hey, here's a quick but important little detail. You've probably heard people call this process triangulation. It's a super common mistake, but it's not actually correct. Triangulation uses angles to figure out a location. What GPS does is use distance from known points, the satellites. And that process is properly called trilateration. Just a little fun fact for you. So the physics and the math have done their job. Your phone now has a set of raw coordinates. Basically, its address in latitude and longitude. But a bunch of numbers aren't a map, right? So let's look at the final piece of this puzzle. How do those numbers become the streets, the traffic, and the coffee shops we actually use? I mean, a set of coordinates is just a point in space. By itself, it doesn't tell you if you're on a highway, in a park, or standing inside a building. To make any of that useful, you have to put it on top of a rich layer of data. You need the digital map itself. These digital maps are really these massive databases with two main parts. First, you've got what's called vector data. Think of it as the skeleton of the map. Every single road is a digital line with a bunch of rules attached to it, like speed limits, turn restrictions, or if it's a one-way street. And the second part? Well, that's the crowd. That's you and me and literally everyone else out there using the map. So ever wonder how your map knows about that traffic jam up ahead? It's not magic. It's actually brilliantly simple. The system just sees a whole bunch of anonymous blue dots all moving super slowly or stopped completely on a stretch of road that's usually fast. It recognizes that pattern, says, aha, traffic jam, and then it colors that road red on your map. It's just crowdsourcing, but on a massive global scale. So let's just step back and put this all together. The next time you're trying to navigate somewhere, just take a second to appreciate the absolutely incredible symphony that's happening behind the scenes. You've got Einstein's physics correcting for time itself bending, you've got a whole orchestra of satellites with atomic clocks in space, and a billion little data points all working together in perfect harmony, just so you can find the nearest pizza shop. It's pretty amazing. And that kind of leaves us with one final thought. We have pretty much perfected knowing our location. It's become this fundamental layer of data for the modern world. But as technology keeps moving forward, what other layers are going to be built on top of it? What comes next, now that we've solved the ancient problem of knowing exactly where we are at any given moment? Something to think about. Thanks so much for joining me.